So technically, if we're going to follow the naming convention we did with our published lecture slides, this would be lecture 6, even though we're in week 9. And now that you guys have a pretty solid understanding about the 1D diffusion equation, that is, we know how to handle the 1D diffusion equation for uniform and non-uniform grids. We know how to handle it for a variety of boundary conditions, whether we have a Dirichlet or Neumann boundary condition. We know how to handle variable area. We had spatially dependent material properties, and we can really easily incorporate, say, temperature dependent material properties. We know how to handle that equation in a steady state and transient formulation. And we know how to compare it to a numeric solver, ANSYS Fluent at the moment. So, although it might, looking back on the class, seem like we haven't done too much, we've covered quite a few topics. So the next logical progression, and what I really want to do is really make sure we have a solid understanding of just kind of the method we're doing and how we're doing it in all dimensions. So today we're going to do the finite volume method. We're going to construct the steady state and transient general transport equation for diffusion with source terms built in. And then we're going to move to 3D. And then from there, we can move into, and this is kind of where I'm torn. We can move into the discussion of, advection diffusion problems. But we can spend an entire class on that because the pressure velocity coupling algorithms aren't the simplest thing, no pun intended, because simple is the predominant algorithm. And it takes some time. So as opposed to, giving you a large breadth of material with a little depth, I want us to kind of narrow focus a little bit and make sure we have a lot of depth in the things we do. So maybe what we can do is then extend our complexity, temperature dependent material properties, a little multiphysics, adding a few other equations in, adding a few other domains in, doing some fun stuff, but I'll figure that out. It really all depends how you guys are doing with your homeworks as well, because that's a good miss test of whether or not you guys are liking this, you're engaged with it, you're doing well with it, or it's now just becoming a nuisance. But with that kind of out of the way, let us kind of resume a traditional lecture style. And today we're going to talk about our diffusion equation in 2 dimensions. So we're going to construct this in 2D. And we already kind of know the basics of ANSYS. So what I'm going to do is we can probably get through the conceptual portion in probably maybe 50 minutes if I talk pretty fast. And now that we've been added to the ANSYS licensing group, big thanks to CRC for that, and working through all those issues. We could potentially do the 2D problem we do in class, just so you guys get a little familiarity with it, a little more practice with it, and that might help out for your homework. So that might be the kind of goal for today, but let's just see how it goes and begin. Now, hopefully by now you recognize this awesome equation, our general scalar transport equation, where phi is going to be a conserved quantity, capital gamma that we typically have used kappa for to define a diffusivity, i.e. our thermal conductivity is in there, and rho is density. So thus far, we've covered all this. And the reason why is this term, this could be multiple classes.
Are you intending to share your screen?
Oh, thanks, Josh. Cool. All right. Now, we should be pretty familiar with this equation. And right now, we've been neglecting convection because that's going to take a lot. Because within convection, we need to be able to apply this equation and really look at the Navier-Stokes equations and recognize that for our problem to be bounded, we typically need velocity specification and pressure specification. And what we see a lot of times is that pressure velocity coupling gets pretty tricky. And then for us to be able to solve it directly, i.e. DNS, direct numerical solution, it becomes computationally prohibitive. So then we have to move in situations of RANDs or turbulence modelings and make some assumptions and simplifications. So we have to go into Navier-Stokes, reduce a whole bunch of things down, then put those reduced equations into a finite volume form, then solve. So hopefully that'd be the second part of this course where we get really into the nitty-gritty of that. But let's now focus on some pretty cool stuff. So what we're going to do is we're going to take the same stencil we used for our 1D diffusion equation, where P is our control volume of interest. And in our 1D situation, we had a cell to our left and a cell to our right that we defined as our east and west cells. And recall W, P, and E, those are our celled centers where we are evaluating our conserved quantity, phi. Now recall, for a uniform grid, delta x is the x width of each of our cells. And delta x west, and we'd also have a delta x east, are going to be the distance between our cell centers. So we had all that previously defined. Now, what's really awesome about the finite volume method is once we have it pretty well developed in one dimension, going to another dimension is super easy. So what we're going to do is to consider two dimensions. We are going to put a cell on top that we're going to call our north cell, and a cell on the bottom, which we're going to call our south cell. Hey, this kind of looks like the cardinal directions: north, east, south, west. That's cool. And what we're going to do is we're going to define delta y as the height of our cell, and we can have two values, delta ys and delta y north, which would be the distance between the cell centers of our south and our center and north cells, respectively. So for this formulation, what we're going to do is we're going to, I guess I'll use that utility instead of the back of the pen. We're going to assume a unit depth. And when we say a unit depth, we're going to assume everything in the z direction is equal to unity. So we did this in the past for a 1D system where we just picked a unit depth. So that's going to be our new stencil. And what we want to do is construct our diffusion equation using this stencil. So it's just a little bit of math, a little bit of derivation, and then we're ready to go. So let us look at our steady state diffusion equation. And there's two ways to think about this. Our steady state diffusion equation, right? We can go back here, set our accumulation to 0, and recall our source terms are just something we tack on right at the end. Nothing too difficult to include. So this tells us that we have the divergence of our diffusion coefficient times the gradient of our conserved quantity. Now, for you guys that are pretty savvy with heat transfer, right, this would be the same as the steady state conduction equation. So you can recall this would be, you'd have the divergence of lambda or kappa grad T, right? And you'd set this guy equal to 0. Now the divergence of lambda times the gradient of T, T is a scalar quantity, right? So you'd have the divergence of this guy, and let's just write it out in the full form. No sense of doing our intermediate steps. We'd have del by del x of lambda del t del x plus del by del y lambda del t del y plus del by del z of lambda del t del z is equal to 0. So in full 3 dimensions, that's what it's going to look like. In 2D, we're going to cut out our z component. So what we did there was just rewrote that equation. So we have del by del x of our conserved quantity, gamma, del phi del x, and we call phi as our conserved value of interest, plus del by del y of gamma del phi del y. and we'd have our source term. Now, what we need to do is integrate over our control volume. So we integrate over our control volume. What we're really doing is integrating between our west and our east cell. We're going to integrate between our south and our north cell, and we're going to integrate between our front and our back cell. Now, we took a unit depth, so we don't necessarily have to integrate over this because it's going to happen on both sides and it's going to divide out. So what we're going to do is do the integral with respect to control volume of our steady diffusion equation. And we've already done this, so we're going to skip a few steps in this process. So what we're going to have is our diffusivity times del phi del x evaluated at our east face minus our diffusivity times del by del x, or sorry, del phi del x evaluated our west face times delta y delta z plus our diffusivity times del phi del y on our north face less that quantity at our south face times delta x delta z. And don't worry about the math. We're going to see this in our example a lot more in depth. And then we have S bar times our volumetric heat generation. Sorry, S bar, which is our volumetric heat generation rate, times our differential volume, delta x, delta y, delta z. And this is equal to 0. Now, what we need to do is recognize that these derivatives, the partials of our conserved quantity with respect to our spatial dimension, we can use a representation of a derivative to re-represent these. And this will allow us to represent it in terms of our conserved quantities within our cell centers. So if we assume we have uniformly spaced cell centers, we're just going to do a basic backward difference. So if we look at this guy, partial phi with respect to partial x, this would be phi e minus phi p per delta xe. So we're going to take, I'm going to jump back here, this value less this value per the distance, delta x east. And then when we do our second derivative, evaluate our west face, we're also going to do a first order backward difference. We'd have phi p minus phi west per delta x west. So if we come here, that'd be phi p minus phi west per delta x west. So those are how we represent our derivatives. And recall they're going to be respectively multiplied by the diffusivity at the interface between our east and cell center and our cell center and our west cell. And we also have this multiplication, delta y delta z, delta y delta z, that came from integrating over our control volume. So that would represent those first two terms of the expression on the previous page. And we can do the same for our remaining two terms. Our derivative with phi with respect to y, the partial thereof evaluated at our north face would be phi north minus phi p. I'm going to jump back here. Phi north minus phi p per delta x north. And then our other derivative would be phi p minus phi south per delta y south. Oh, that's a y, not an x. So we'd have our delta y north corresponding to our backward difference between our north cell center and our center cell center values. Then we have a delta y south underneath phi p minus phi s. And once again, these are going to be multiplied by the respective diffusion coefficients at the interface. Now note we have two new diffusion coefficients, phi n and phi s. And we also have to recall that when we integrated this with respect to our control volume or differential volume, we're going to be left with delta x and delta z for these terms. And last but not least, we have our volumetric heat generation term. So we can expand everything out, which we do here. Just expand out what's within the parentheses. No need to go over that. And we're going to group like terms. So now what we have is a conserved quantity in our east cell, a conserved quantity in our west cell, a conserved quantity in our north cell, and a conserved quantity in our south cell. All of these now get added to the conserved quantity within our cell center. And when we do this, we see something relatively familiar, right? If we were looking at delta x east, in this particular situation, we have our diffusivity in our east face per the distance between our two cell centers. And if we go back a lecture, let me pull this up. I'm actually going to go back quite a few lectures. Lecture 3. Yeah, and this would be multiplied by our we took into account our area previously, so we were able to just normalize that to unity. We have a very similar expression. Whoops, let's get the eraser out. Where we have our diffusivity, basically a cell height, and our difference between our cell centers. Now the only thing is, we're just adding one other dimension to this. So it looks incredibly, incredibly similar to what we've seen in the past. We can recognize everything in this parenthesis. We can group it together as a coefficient. So what we have is if we define A east as a diffusivity of our interface between our P and E cells per delta x east per delta y, times delta y times delta z, this will be A east. And for us to draw a parallel, in 1D, we had A east defined as the area of our eastern face times our diffusivity per delta x east. So it's delta y, delta z. What this is looking like is our delta y, delta z. Once again, our area to that interface. However, we're not just specifying it as a value. We're actually able to define it based upon our cell sizing now, i.e. we're kind of incorporating that dimensionality. So what we see is our coefficient to our conserved quantity, phi of east, which we define here as A east, is really no different than what we did for our one-dimensional case. We just re-expressed out area as opposed to tacking on as a single term. And we can go through and define the rest. We'd have a coefficient for phi west that we'll define as A west right here. We'd have a coefficient for phi north that we'll call A north defined here. And what we'll also have is a coefficient for phi south, which we'll call A south defined here. Now, what's cool about this is phi p, previously in a 1D case, phi p was going to be dependent upon A east and A west, where we said AP was simply equal to A east plus A west. Now, in this particular situation, we see we have A east, A west, A north, and A south included. So we can modify what we define as AP. So through this process, our equation really hasn't changed. All we really need is an update to definitions of our coefficients for our conserved quantities. Namely, we need to update A east, A west, A north, A south. And then when we calculate AP, which leads phi p, we just have to include our new neighbors to the north and the south. So it's really a slight modification going from 1D to 2D. Now, with all that fun stuff being said, we have something that we'll talk about a little later in class, not this class, probably next class, is our volumetric heat generation rate. So we multiply this through by our differential volume. And what we do is for S bar, we define it as a linear contribution and a nonlinear contribution. So SC would be a constant source, and SP Vp would be a source that's dependent upon the temperature of our cell center within the center of our stencil. And we'll talk about source term linearization next class and how we handle nonlinear source terms, which is pretty cool. And what we're going to do is define, since that is going to represent this term right there, what we're also going to do is define B as all this multiplied through. So that is really, in essence, just a dummy placeholder that makes life a little bit easier, as opposed to multiplying all that through. But in its final form, we can say the coefficient AP is now going to be equal to A east plus A west plus A north plus A south. So we added our two neighbors right here. And what we can also do, and this is going to be important when we consider source terms, is we can take the nonlinear contribution of the source term and group it in with our coefficient to Vp. Now, you can think of a nonlinear source term as something that might be dependent upon temperature. So joule heat, right? That's your current density squared. So your current density vector times your current density vector, actually dotted, which gives you a scalar value, the magnitude. The magnitude of that value times the electrical resistance of the cell. And your electrical resistance is based upon your electrical resistivity times the length of the particular element per the area of the particular element based upon the direction the current's flowing. That electrical resistivity is oftentimes dependent upon temperature. So we could bring that in as a nonlinear contribution. It's not a constant contribution to your source. So we can break out terms like that into our AP coefficient, which is incredibly helpful. So once we do all that, our general scalar transport equation for 2D diffusion for steady state is going to be expressed as this. We'd have AP Vp is equal to A east V east plus A west V west. All of this looks really familiar right now, right? And the only thing we did is we tacked on A north times V north plus A south times V south. And then we added B, which was just our constant source term, times our differential volume. So really, the finite volume method is super, super easy. If we have a good understanding of the 1D case, as we move to higher dimensions, it's not going to take a really more difficult form. There's not going to be any more complex mathematics associated with this. We just kind of tack on the additional stuff we need. Now, you might be wondering, okay, that's a pretty simple way to construct this, but how do we incorporate our boundary conditions? And if any of you guys have taken Professor Givey's computational analysis and transport phenomena course, this might be at the back of your mind because this is one of his favorite problems. You kind of have a pizza slice where you take a little bit out of this corner, and this edge of the slice might be held at one temperature. this edge of the slice might be held at another temperature, and then this might be adiabatic or at another temperature. And what you see is when you're doing this problem, in that course, you learn really how to apply the finite difference method to diffusion problems, as well as using stream functions and the finite difference method to handle diffusion problems as well. And what you guys notice is when you do the finite difference method, you have one node down here, right at this bottom location. And you go, okay, that node, it can't take two temperatures simultaneously, right? This might be 300 Kelvin. This might be 200 Kelvin. And that node, you go, well, what's my temperature going to be? And you find that, you can't average them because that changes the solution. You can't alternate between which value it is depending upon what you're solving because you're never going to get convergence. And what you have to do is just ignore that node. So for axisymmetric problems, that's tough. In this pie slice problem, you lose information down at that corner of the pie. But with this, we can actually cover that because we're not evaluating our equations at our vertices, we're evaluating at our cell center. So this makes the application and incorporation boundary conditions a little more robust. So let's consider a two-dimensional system. Now, here is our differential volume. And let's pick a more fun color. So this is the face we're looking at. So say this is our cell center P, where we have a size delta x and measuring our distance in the x direction, delta y measuring our height in the y direction, and delta z was just our unit depth, but we keep that for robustness. Now, what we see here is if we look at this, here is our box, here's our cell center. Now let's draw this in a slightly less complicated formulation. So if we want AB, right? And let's imagine there's actually just a whole bunch of boxes like this. And everything to the left is a boundary temperature. So what we saw in the 1D finite difference method is we know our boundary temperature, which is Pb. And when we evaluate this, our delta xe, our distance from our celled centers, or actually this would be delta x west, is just simply delta x per 2. So all we have to do is take the diffusivity at our boundary and divide this by delta xb, which we can denote as just the distance between our celled center to our boundary, which is the same as delta x west in this particular situation divided by 2. But what we do is carry over our same delta y and delta z that represents the area. So if we have a singular boundary condition on the left-hand side or right-hand side or top and bottom, it's super easy to incorporate. We incorporate it just like we did in our 1D diffusion equation. And what we do is if this is a temperature, we just add AB Phoebe to B, which was our catch-all term. So you could also do plus AB Phoebe as we did in the past when that's evaluated at our boundary. If we have a nonlinear contribution to our source term, we just add AB to AP as well. And then we would remove our coefficient in this direction. Since this is to the left, we would remove a west. We'd set that to 0, and we'd set this to 0 since we're evaluating AB Phoebe. So the same procedure we did in the past. And if we had a flux condition, we do it the same way. All we have to do is specify that flux at that particular location. So the cool thing about this is, your flux is just the negative of your diffusivity times del phi del x evaluated at your boundary. So, and we know this has to be equal to 2 phi b delta y delta z times, or per delta xb, because that's just conservation of heat within that situation. So in that particular situation, you can just reevaluate this as we've done in the past. I think that was lecture 4. Yeah, let me pull that up. Temporal, volumetric terms, convective boundary conditions. Example 2, we did a lot in lecture 4. Might have been even lecture 5. It's all beginning to run together. It was in one of those. So in that particular situation, we'd recognize that, okay, at our boundary, our heat has to be conserved, right? R2 gamma b delta y delta z per delta xb, which was here. For us to conserve heat, this has to be equal to J, our flux, which is represented by this expression. So on our previous slide, we defined AB as 2 times gamma b delta y delta z per delta xb. Now we just replace that with our flux. So our flux, recall, is a quantity in terms of heat per meter squared. We multiply it by our area. And that will give us our flux boundary condition. So as opposed to adding AB, we just add J, our flux, times the cross-sectional area it is flowing through. So the incorporation of a Dirichlet-Neumann boundary condition in this formulation is no different than our 1D diffusion case. Now, this is where I was kind of talking about kind of the failure of the finite difference method when you have that pi slice. So let's re-express this face right here just in a 2-dimensional format. Say you have your cell center. Say we have one boundary condition on the left. Blue is going to represent one boundary condition, and then we're going to have green representing another boundary condition. Now, if this were the finite difference method, you'd be solving for your values at your nodes. And as we said, that's really hard to do because that node is simultaneously taking 2 values. So technically, we'd have to ignore it to be able to solve it. But what we do here is we just define 2 unique coefficients. AB1 would be 2 times phi b1. So we'll call this guy phi b1, our conserved quantity at boundary 1, times the diffusivity at gamma b1. So that'd be our diffusivity, and we could do b1 there, times delta y delta z, which gives us this area per delta x, which is, we don't really need to designate that as a b. You can do it if you want to. You could call it delta x as well. So that would really represent our same coefficient for our boundary conserved quantity that we did when we weren't considering a boundary condition above or below. And then all we have to do is define a second boundary condition down here. And we're going to call this AB2, which is going to represent phi B2. And what we do is take 2 times the diffusivity at this bottom boundary interface, that's gamma B2, times delta x delta z, which is representing this green face right down here, the area at which this boundary condition is being applied per delta y. And delta y, you can think about this as the height of your cell. So we can simultaneously consider both boundary conditions and their influence on our cell center volume with no major modification and no other derivation. And all we have to do is modify B, which includes our boundary condition. So we can say right here, B star would be equal to B. You recall B had our linear contribution of our volumetric source term, i.e. the constant. This was SC, delta X, delta Y, delta Z, plus AB1 phi B1 plus AB2 phi B2. So what's super awesome about this is you can simultaneously consider 2 boundary conditions acting on different sides of a cell. The finite difference method, although it's very, very robust, I love the finite difference method because you can do super high order schemes really, really easily. You get into problems with pie-shaped slices like this. Any axisymmetric problem, if you're not doing the whole revolution, it gets really, really tough. So sometimes it doesn't allow you to capitalize on the symmetry of the problem. So those boundary conditions are pretty cool, and the treatment of them. If you have a flux, this is super easy, right? You just add the flux times the area at which that flux is crossing to each of your respective terms. So if you had a flux, you'd have B star is equal to B, and let's just call this JB1. And let's imagine that's happening on boundary 1, and you would just multiply this by delta Z, delta Y, plus JB2. Let's call it JB2 entering here, and this would be by delta Z, delta X. And that's how you handle a flux. Or if you want a flux and a temperature, you can include your temperature term here, drop this, throw in your flux there. It's so easy, it's so adaptable, there's no rederivation, it's just kind of picking and choosing the expressions you already developed. That's pretty awesome. So although we went a little bit quick over this, we've seen all these equations before, we've seen all these coefficients before, we've seen the incorporation of all these boundary conditions before into our algorithms. So this is nothing more than just tacking on a few additional terms to our 1D diffusion equation. It's awesome. Now, with that, I think this is a pretty decent time. Oh, no, we got 2 slides left. Let's do those and then we'll take a slight break. So, there are just a few things you have to consider though. This is really nice because we have our coefficient AP leading our conserved quantity phi p, and we know AP is equal to A east plus A west plus AN plus A south minus any nonlinear source term contribution plus any nonlinear boundary condition contribution. And this is equal to all this stuff on the right-hand side. So we could conceivably solve for phi p. Now, the difficulty with these types of problems is it doesn't lend itself, especially when we start doing transient problems and the like, to the simplest implementation of matrix inversion. Oftentimes, there's other easier methods to code in to use to solve. I'm not saying you can't do a matrix inversion. You're just going to have some fun time doing a little bit of manipulation. But let's look at an example here and see how we could actually come up with some schemes and methods to solve a 2D diffusion problem. So let's imagine we have a 5x5 grid. So what we have here is 5 control volumes in the x direction, 5 control volumes in our y direction. So we're going to have 25 control volumes in total. And our cell centers are going to be denoted by those black circles or black dots. Let's imagine we have 4 unique boundary conditions. And each of those boundary conditions is existing on each of the cells. So we can color in the top as yellow, the left as red, the bottom as blue, and then the right as green. Now we know in this particular situation, for us to define those boundary conditions, if say they are all Dirichlet boundary conditions, we're going to have 7 unique temperatures in the x direction, 7 unique temperatures in the y direction, because we need 2, 1 on each end of our domain, in addition to our cell centers. So we're actually going to have 7 unique conserved quantities in the x, 7 unique conserved quantities in the y, if you look on a per slice or per column basis. And that's going to be denoted by I and j. So j down here, this is counting the number of conserved quantities. So this would be j is equal to 1, j is equal to 2, j is equal to 3, 4, 5, 6. That'd be j is equal to 7. Now, as we move, say, down the y direction, we'd have this being I is equal to 1, 2, 3, 4, 5, 6, 7, going down this way. So that's important to keep track of that in our domain in our solution, just because we're going to be pulling some of our boundary temperatures. Now, there's 2 easy ways to do this. And I say easy because it's super simple to program in. You can do Jacobi iteration. So what we would do is go through our domain. And for j is equal to 2, and I think this is supposed to be n plus 1. Yep, because that would give us 6. And for I is equal to 2 to n plus 1, we would have phi of p of k plus 1 would be 1 over ap. And then we'd have all our coefficients, a west, a east, a south, and a north, leading all our conserved quantities, phi west, phi east, phi south, and phi north, all taken at the previous iteration, plus b, that catch-all term. Now, we saw the Jacobi iterative method. Really, we take all the information from the previous level and use it in the next level's calculation as an iterative solution. And recall, Gauss-Seidel is a little bit fancier. For the Gauss-Seidel method, we had the same looping scheme, but now in our formulation, as we move through our domain, we can kind of propagate the information from phi west from our previously calculated cell. And what's cool about this is you get a slightly faster solution because you're propagating a little more of the information through your domain quicker. Additionally, I think as we move through, don't quote me on this because I haven't tried it, but this says we're moving from west to east. This says we're moving from north to south. We should be able to take our previous iteration level there as well. So you'd have an phi of n to the k plus 1 if we had that solved. So as we move through, you can take what was previously solved to your left and above. But those are 2 pretty robust methods for moving through the system. You can try and cast it into a simultaneous system of equations and do the inversion process. It just gets a little bit messy. So I was going to show you guys these 2 solutions to our system, and we're going to use one of them in our example today. So kind of in summary of the finite volume method in 2D, it's no different than casting our diffusion equation of finite volume method in 1D. Update our coefficients, go through the same solution process. So with that, let's take a little break. Let's resume at say 5:25. Give you 9-10 minutes. Stretch your legs, get something to drink, and we'll come back and go through an example. We'll go through, do the derivation for the example, talk about how the form of solution takes, and we'll take a look at the MATLAB code. So as mentioned, for those that will be viewing this recording, based upon the way we have our I and j loop set up and how we are really indexing through our domain, sometimes it's easy to modify which of the values, either phi west, phi east, phi south, or phi north, we are taking at our iteration level within the Gauss-Seidel iterative scheme, as well as what location we want to take them at. So I'll double check this, and based upon the convention we set up on slide 12, update the slide to what would be the fastest and best way to speed up our convergence using the Gauss-Seidel method. So with that, let's look at, oh, I forgot one other thing. How do we solve our system of equations? Well, we outlined the Jacobi Iterative Method, which is just solid, right? We had the Gauss-Seidel method, which is pretty good as well. And we also talked about, previously, Tdma, and that was for a tridiagonal matrix. Now, what we can do is really modify Tdma for a pentadiagonal matrix is what we'd have. And there's something called the pentadiagonal matrix algorithm, Pdma. However, there is a paper from, and I think it's late 70s. No, Pdma. I think this was early 90s when this was published. The pentadiagonal matrix algorithm, where it's really just doing a fixed point iteration, where you're trying to get only one term on the bottom row of your coefficient matrix, because then if you look at your solution matrix, you know what that guy is going to be equal to. And then you solve your way backward. So the Pdma method works. However, no text I found provides an example of it. But I think this would be something fun if you're interested in doing. I could steer you to the paper that outlines it, and you can give it a try and see if it's faster than matrix inversion or some of these iterative methods. So typically for these 2D systems, yeah, we can do our iterative methods, and we could just do brute force matrix inversion. But recall, for our 1D system, we saw when our system got large enough, that Tdma was so much faster than a standard matrix inversion algorithm because it's not operating on all those zeros. So if your research goes down this avenue and you're building your own codes, your own in-house stuff that you're going to use repeatedly, Pdma might be something to look into. And once we move to 3D, you're going to have a septadiagonal matrix because we're adding our front and back terms. And then, you could have an SDMA algorithm as well. But, Pdma is the only thing I've seen in literature. But I don't know if all that work of developing your own scheme really outweighs just computation time. That's one thing I like about numerics. When a big problem solving it's taking a couple days, you can justify why you're being lazy. And also supercomputers help because you can run a whole bunch of different jobs simultaneously, as opposed to waiting for one job to come in, then running another. But if you are interested in those algorithms, I'll definitely share that paper, and you can look into it a little further. What we're going to do for this class is just use some of the basic iterative schemes because those are super simple to code into MATLAB, and you guys are pretty familiar with them thus far. So let us now look at an example of a transient 2D diffusion problem. So we're actually going to have a little bit of fun. So let's imagine we have a 40 centimeter by 40 centimeter plate. And we're going to find our thermal diffusivity as 0.97 centimeters per second. And this system is initially at a temperature of 100 degrees centigrade everywhere. Then once time t is equal to 0, we expose our top, our left, our right, and our bottom sides all to a temperature of 0 degrees centigrade. Is that what I did in the script? Let me look. Yep. Yeah. and we're going to set this to 0 degrees centigrade as well. That's a really simple modification within our code. So let's put everything 0 degrees centigrade. Now, what we want to do is look at the evolution of our temperature as a function of time. So our temperature is going to be a function of x, y, and t. And what we want to do is look at some discrete time intervals, 10 seconds, 15 seconds, 30 seconds, 50 seconds, 100 seconds. And we also want to determine the time it takes for our system to reach maximum temperature of 10 degrees centigrade. Okay. So although this is a pretty basic problem, it's good for us to develop our code and benchmark it against something we know we have a solution to. And an analytic solution does exist for this problem. So what we'll do is proceed with the following. Thus far, we've constructed our steady state two-dimensional diffusion equation and a finite volume formulation. But now we have to do our transient equation. So our transient diffusion equation will take the form: our density times our specific heat times the partial of our temperature with respect to time will be equal to the divergence of our diffusivity times the gradient of temperature. If this is steady state, this goes to 0, and we have the same solution as we did before. But now we need to consider our temporal term. So in 2 dimensions, we're going to recall that the divergence of our diffusivity times the gradient of temperature gave us 3 terms that were added together. We'd have del by del x of our diffusivity times del t del x plus del by del y times our diffusivity times del t del y. In 3 dimensions, and if you guys want to get ahead and get bored and derive this for 3D, you would just tack on del by del z of our diffusivity capita del t del z. And we throw that guy on the end. But for this, we're going to focus on 2D right now. So what we need to do is recognize that we need to apply this equation to a control volume. Recall our control volume is going to have a length in the x direction, delta x, a height in the y direction, delta z, and a width in our z direction, delta z. So we need to integrate over our volume, and we also need to integrate over a period of time. In that period of time, we're going to go between t and t plus delta t. So for this, we're going to assume you just have a unit depth in our system right now. And we're going to express that guy. You can express as unity, or really, we can just keep it and see how it plays out in the end. So for us to start, let us take the left-hand side of our diffusion equation, rho c del t del t. Now recall, t is a function of our x location, our y location, and time. So that has to stay on the inside of our integrals. And rho and c, we're going to assume constant, so they can come outside our integrals. So we're going to have rho c. We're going to integrate from west to east, south to north, t to t plus delta t of our partial t with respect to t. And then what we're going to do is make sure what we're integrating with respect to lines up. So we have our dt corresponding to our integration over time. We have dy corresponding to our integration bounds within our y direction, south to north. And then we're going to check that we have dx lining up with our integration from west to east. So that's going to be our left-hand side. Not too bad of an equation. And then what we have here is right-hand side. Now note that we had 2 terms. We have to integrate each over our volume and with respect to time. So we're going to put time on the outside. So we're going to integrate from t to t plus delta t. I'm going to integrate from west to east and from south to north of the equation del by del x of our diffusivity times del t del x. And we see the what we're integrating with respect to. North to south is dy. West to east is dx. T to delta t is with respect to time. And we're going to do the same thing, except we're just going to switch our bounds of integration. It doesn't matter because what you're going to see momentarily is how this plays out. So we're going to integrate from t to t plus delta t. That'll be our outside bound of integration. From south to north, and then from west to east, del by del y times the quantity, or operating on our quantity, our diffusivity, del t del y. So we have this integral differential equation that we want to solve. We have some derivatives and some integrals all mixed together. Now let's look at our temporal term first, because we have pretty good experience with this from lecture 4. So rho and c are constants. And in this particular situation, we are integrating t with respect to t. So we have no y in this equation, we have no x in this equation, right? So our outside integral, we're integrating from west to east of dx. So we just plopped out an x, and we're going to evaluate it between the bounds of east and west. On the inside, we have no y within our equation. So we just tack on a y, and we're going to integrate from south to north. And what happens here is when we take the integral from t to t plus delta t of del t dt, that just gives us dt, our change of our temperature evaluated between the bounds of t and t plus delta t. So what this gives us is we would have rho c, our density, times our specific heat, times x at the east face minus x at our west face per this term right here. And then we would have, whoops, that's a y, my apologies, y at our north face minus y at our south face, which represents this quantity right here. And this would be times the quantity, t at our solid center, p, evaluate the time t plus delta t, minus t of p, evaluate at time t. Now, x at our east interface minus x at our west interface gives us delta x, the width of our cell. Y at our north interface minus y at our south interface gives us delta y, the height of our cell. So our temporal term reduces to our density times our specific heat times delta x times delta y times the quantity t evaluated at the cell center of our center cell p at the time t plus delta t minus t of p evaluated at time t. So if we go to lecture 4, let me pull this guy up. And I'll steer you guys to that slide. Slide 8, lecture 4, slide 8. We had rho c delta x, t of p at t plus delta t minus t of p at t. Right? Nothing's really changed, just the fact that we integrated with respect to our y direction now, and we have a delta y hanging out. Nothing too crazy. So I really love the finite volume method because if you have a strong foundation, you can just build off of it really easy. Okay, now that covers our temporal term. We need to handle our spatial terms. And this is where stuff gets fun. So let's look at the right-hand side of our diffusion equation. Now, let me note why we did what we did. So here is our integrand. It's what's inside our integrals. This guy isn't dependent upon y, right? We got del by del x operating on kappa del t del x. So if we integrate this with respect to y, we're just evaluating y between our north and our south face, right? And then all we're left with is our temporal integral hanging on the left and our spatial integral. And we know how to handle the integration of del by del x of the quantity kappa del t del x, also from lecture 4. So what this becomes is we have the integral from t to t plus delta t of the quantity kappa east, t east minus tp per delta x east minus kappa west, tp minus t west per delta x west. That was exactly what we did in lecture 4, slide 9. Of how we got that expression. Then we had our y from our inside integral evaluated between our north and our south face. And I'm sorry I wrote x. This is a lot to type up, but I'll fix that. So you'd have y to our north minus y over south, and this is delta y. And then all we have to do is evaluate this integral with respect to time. So we took care of the temporal portion of it thus far. And then the second term of the right-hand side of our diffusion equation, if we jump back here, we have del per del y of the quantity kappa del t del y. This is our integrand, and there's no dependent upon x. So if we integrate this with respect to x, it's going to be x evaluated between our east and west interfaces. And then we just integrate from our south to north face of del y. Our del y's kind of cancel out, so you'd have del kappa del t del y. We know how to handle that integration from lecture 4. So that turns into kappa, evaluate our north face times the quantity t north minus tp, and I'll fix that. There's a lot to type up this morning, per delta x north minus kappa s times tp minus t south per delta x south. And we have this quantity that was hanging out. This is x evaluator east interface minus x evaluator west interface, which is delta x. So now all we have to do is integrate this guy with respect to t, evaluated between our bounds of t and t plus delta t. So right now, if we do a comparison to lecture 4, and we look at slide 9, the only thing new from 1D is this delta x, sorry, that delta y, and this delta x. Everything else is the same. That's nice. That's really nice. Now, what we're going to do is when we do our integration over time, we're going to introduce our weighting factor, f. And recall we did the weighting factor because we were able to define an explicit scheme, an implicit scheme, the Crank-Nicholson scheme, which sets the weighting factor to 1/2. And you could also think of this as a relaxation factor, and you could pick the proper weight that allows your system to converge the quickest. But that does a little, trial and error values of f you select. So what we do here is we just introduce our weighting factor. And once again, lecture 4, slide 9, where we said the integral from t to t plus delta t of t of p dt. We said this was equal to f of t of p, t plus delta t, plus 1 minus f t of p evaluated at t times our time step, delta t. So f allows us to take a contribution of our current solution, our previous solution, either or, however you want to do it. So in doing that, all we have to do is apply that formulation. So our first term on the left-hand side here is integral from t to t plus delta t of everything within this big parentheses times delta y dt. And what this gives us is the following. We'd have our weighting factor, f, times the quantity, our diffusivity at our east interface, times the quantity, t east, evaluate at t plus delta t, minus t of p, evaluate at t plus delta t per delta x east, minus our diffusivity, evaluate our west interface, times the quantity t of p, t plus delta t, minus t of west, t plus delta t per delta x west. Multiply that by our delta y that we had there, and we have our delta t. And then all we have to do is consider our contribution from our previous time step. So we'll have 1 minus f, our weighting factor, and we're going to have the same expression. However, we're just evaluating it at our previous iteration level, our previous time step. So we'd have our diffusivity at our east interface, t east at time step t, minus tp at our time step t per delta x east, minus our diffusivity at our west interface, tp at our time step t, minus t west at our time step t per delta x west. And this is per delta y delta t. So this represents the first term on the right-hand side of our diffusion equation. Which isn't bad. Now we do the same thing for our second term. And what we're going to have here, and I'll update this, we would have plus f times the diffusivity at our north face, which is kn. And then we're going to have tn evaluated at t plus delta t minus tp evaluated at t plus delta t. And then we subtract our diffusivity at that southern face times the quantity tp plus t plus delta t minus ts evaluate t plus delta t times delta x delta t. And then we consider our weight from our previous time step. So it's the exact same expression above. Now we just evaluate our conserved quantities at our previous time step. Once again, delta x delta t. This was the second term from the right-hand side of our diffusion equation. There's a little bit of a few terms to keep track of, but not too much different, right? The only thing new we've added from our 1D diffusion equation is everything below this dashed green line. And it's very formulaic. It follows a pattern. So what we're going to do is go back to our diffusion equation, right? Because we broke down our terms. This was initially our equation. We expanded it out. We did our temporal term here and got that solution in this giant mess. So that's, our temporal term and a finite volume form. And this is our spatial term in a finite volume form. Now we just set them equal and start going through the process of solving for TP, evaluated at time t plus delta t. So I put all that together right there. And now I'm just going to go through and make sure I didn't have that one mistake from the north and south. So what we're going to do is divide out by delta t in group-like terms. So I'd encourage you guys, take a big piece of paper, write this out if you want. Our first term here on our temporal side is we have t evaluated at cell center p at time t plus delta t. And this is multiplied by rho c delta x delta y. And we're going to divide that by delta t. So that's going to be on the left-hand side. And then here, we can go through and count our TP of t terms. So we have 4 of these guys. So we're going to move them all over from the right-hand side to the left-hand side, and they're all negative. So we just add them. So we're going to have f times this big summation, because all these guys were multiplied by f. Diffusivity of east interface, delta y per delta x east, plus the diffusivity of our west interface, delta y per delta x west, plus the diffusivity of north interface times delta x per delta x north, plus the diffusivity at our south interface times delta x per delta x south. So all these terms are leading TP of t plus delta t. Cool. Now you also have TP of t, i.e. from your previous iteration level, multiplied by rho c delta x delta y divided by delta t. And we have a few of these guys hanging out as well. Here, 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 and here. Those are all from your previous iteration levels, and they're all multiplied by the quantity 1 minus f and their respective diffusivities and spacings. So we can come down here and group all these guys together. T of p, evaluate at t, you'd have rho c delta x delta y per delta t minus 1 minus f. It's going to be multiplied by this quantity. And you can go through and group those like terms. Additionally, you have your east, your west, your north, and your south conserved quantities, all multiplied by their respective diffusivities, spacing of your cell, distance between your cell centers, evaluated at your respective iteration levels, and multiplied through by your weighting factors. So this looks like a mess. It kind of is, but it's all algebra, right? We did all the nasty integration previously. So this is the complete form of the 2D transient equation. So that's a fun guy to work with, right? No, what's super awesome about this is we can determine what scheme we want to use. That is, do we want to solve this using an implicit scheme? Do you want to solve it using an explicit scheme? Or do you want to solve it using a Crank-Nicholson scheme? And you can decide. You have now the ability to go through and assign what value you want for f. And then go through and just populate your terms and go through an iterative solution methodology. So what we'll do for this example is we're going to assume our scheme is going to be explicit, the slowest of the schemes. So if it's explicit, our weighting factor is going to be set equal to 0. So if it's explicit, that drops out. And that means we're going to take everything from our previous solution level. So all those terms drop out. 1 minus f, this goes to 1. And what we're left with is we'd have rho c delta x delta y per delta t being the leading coefficient for the conserved quantity at the center of the cell we want at our iteration level t plus delta t. And what we see is this is k east delta y per delta x east times t east at our previous iteration level, plus k west delta y delta x west, t west at a previous iteration level, kn delta xn, tn at a previous iteration level, plus ks delta x south, ts at a previous iteration level. So that's grabbing our neighbors from our east, west, north, south. And then we just take the solution from our previous iteration level directly below. So we'd have Tp of t, and this is multiplied by rho c delta x delta yt, minus the quantity k east per delta x east plus k west delta x west delta y, plus k north delta x north, k south delta x south delta x. That's all grouped together. So that's if you have an explicit scheme. It looks bad. It's not, because if we're kind of lazy and we assume everything has the same diffusivity, that is, we can set k east, k west, k north, and k south. I'm calling it k as opposed to kappa. It's just a little faster. It rolls off the tongue a little better. I think I said kappa probably 100 times already. If we set them all to the same, we can just define as kappa. And if we define a uniform grid within the system, we'd have delta x east is equal to delta x west, which would just be equal to delta x. And we could say delta x north and delta x south would just be equal to delta y. So we can make those assumptions. The uniform grid, yeah, that's easy. I could totally agree with uniform grid. Diffusivity, cool. If it's constant, we don't care about that. Valid assumption. So then we'd be left with rho c delta x delta y per delta t tp, evaluate t plus delta t. And this becomes k delta y delta x, t east plus t west, evaluate our previous iteration level, plus k delta x delta y, times t north plus t south, both evaluate our previous iteration level, plus tp of t. We'd have rho c delta x delta y per delta t minus 2 k delta y delta x minus 2k delta x delta y. So it reduces down to something really nice and manageable. And last but not least, we're going to define our thermal diffusivity as our thermal conductivity per the quantity of our, well, we're going to divide it by the quantity of our density times our specific heat. Thus, we can express Tp of t plus delta t would be alpha delta t per delta x squared. T east plus t west, evaluate our previous iteration level, plus alpha delta t, divide this out by delta y squared, times t north plus t south, evaluate our previous iteration level, plus tp. Now that should be a lowercase. I'll fix that guy as well. Evaluate our previous iteration level, times the quantity 1 minus 2 alpha delta t, divide out delta x squared. And somehow I lost minus 2 alpha delta t per delta y squared. So I'll make all those little typographical changes. My bad. This is just too much to type up in LaTeX in one sitting. But that's a solution. So with those assumptions and picking an explicit scheme, we go from something that looks like this, which actually isn't horrendous. I think it's a slightly smaller equation than writing out Navier-Stokes in 3 dimensions for a cylindrical coordinate system. I think there's fewer terms, to be quite honest. And most of you guys have mastered Navier-Stokes and Cartesian and cylindrical coordinate systems, so this is cakewalk. We're left with this really nice, simple expression. And this, in its entirety, is your transient 2-dimension diffusion equation. Now, you say, but what about source terms? Well, we just kind of tack those on. If you have a volumetric source term, we just tack that guy on. We just throw S onto there. when you integrate that guy, you're just going to multiply it by your differential volume, and you're going to integrate it over delta t. So that delta t, that all gets divided out. So really, at the end of the day, you can just tack it on and you're done. I love the finite volume method. It's the one thing you're like, oh no, I forgot a term. Let's just throw it on to the end, and it works. Probably why industry likes this so much. They always forget about things and throw it on right at the end. So that's the rundown of the derivation and how we can really employ our method to generate the equations we need. So the transient takes us form. The steady state much nicer form because we just have our coefficients, throw it into a matrix, solve it, you're done. But let's look at how this solves. Let's get Zoom fired up. Okay. So I stole Bailey's code once again because she writes code so much nicer than I do. So here is our problem statement. Now, what we have provided is starting on line 24 of your lecture 6 example1.m file is the analytic solution. So we picked an example to run through that you can compare directly to a pretty well accepted mathematical solution. And a reason for this is, you always want to test your codes out to something you know the answer to. Flush out any kinks. So we have our analytic solution that takes the form of a equation where you do separation of variables and we just sum up over a distinct number of eigenvalues. So line 24 down to line 66. This gives you the analytic solution. So you can evaluate this particular solution just by coming on down into your blue region and hitting Control-Enter on your keyboard. It'll take a moment. There's quite a few eigenvalues that are summed over in this particular situation. And we'll get a surface plot of what the analytic solution will look like. Then we're going to talk about the implementation of the finite volume method and see what that solution looks like. So we'll give it a moment. The analytic solution takes a good portion of the time as well as getting it to plot. So I'd encourage you, pull down that script yourselves, crack open MATLAB, give it a whirl. You can see what's happening side by side. There we go. There is our analytic solution. Nice contour plot for our discrete times. And what we have, is situation right around 239.8951 seconds is when this particular slab cools to a maximum temperature of 10 degrees. So let's see how our numeric solution is going to compare. So what we're going to do is in this particular problem, n, the number of control volumes, was set to 100, and we need n plus 2. Basically, let's call them nodal points. So we're going to have our n control volumes and 2 on each end for boundary temperatures. So we'll define our x domain, 40 centimeters in each direction, and delta x and delta y. That would be the triangle delta. It would just be x per n. So that's going to give us the width of our cell and the height of our cell. And we'll set delta z equal to unity. Now, del x, del y, and del z, since this is going to be a uniform grid, we'll just set those equal to delta x, delta y, and delta z. So we can populate our cell centers, going from 0 plus del x per 2 to delta x to x, the end of our domain. And we can also define our grid points or nodal points. So that will be enough for us to have all the pieces of information we need. Awesome. The initial conditions within our system, our temperature is initially at 100 degrees centigrade. So we'll specify ones to all nodes within our system. So our ones vector is going to be in n2, which was just n plus 2. And then temperature where x is equal to 0 and x is equal to L is going to be 0 degrees centigrade. And then temperature for where y is equal to 0 and y is equal to L is also going to be 0 degrees centigrade. And then we can specify those boundary temperatures along the edges of our two-dimensional domain. So that'll give us our domain initialization, the application of our boundary conditions. Line 125 gives us our thermal diffusivity. And analytically, we know we need about 289 seconds. So we'll set our total time to 300 seconds. Now, this is where you guys have to pick a delta t. For an explicit scheme, right, we want that wonderful leading term, our alpha delta t per delta x squared. And we also need to consider alpha delta t per delta y squared hanging out here. We want those typically to be minimum less than a half. Typically, a quarter is a pretty good value. Even lower, the better. So you could actually calculate this, right? Alpha delta t times or divided out by delta x squared should be less than a half. So you'd see delta t should be less than delta x squared per 2 alpha. So let's try this. And we will actually print that out when we run and see what value we get. Now that's really your minimum. You'd also want to compare for delta y squared in the situation where you have a non-uniform grid. And then we just determine the total number of time steps we need. And within our solution that we saw in our lecture slides, we had a situation where we have our alpha times delta t per delta x squared. And this appeared multiple times. It led our t east and t west conserved quantities, and it was within our TP expression. So we'll define this as K1. K2 will be alpha times delta t divided by delta y squared, because that appears. So you can define this as an arbitrary coefficient. So if we go through an explicit scheme, all we have to do is employ the same Jacobi Iterative Method that we saw before. So we're going to go from j is equal to 2 to n plus 1, and I is going to be from 2 to n plus 1. And our temperature, this is T of P, at ij of our time step plus 1. And we'd have the following expression. We'd have 1 minus 2 times K1 minus 2 times K2 times our time at ij, which is our cell center, our previous time step. This is going to represent this term right here in the cursor on the right. They're going to have plus K1, which is representing alpha delta T divided by delta X squared. We're going to have temperature I minus 1, which is our west cell. J at time step, which is our previous time step, plus temperature of I plus 1. This is our east cell. So this represents the first term on the right-hand side of our final expression. Last but not least, we're going to have K2 times T of I, J minus 1. This is our south cell, plus T of I, J plus 1, north cell. That guy. And the reason why we're going from 2 to n plus 1 is we already had the boundary information. That was predefined in our boundary conditions. And then all we have to do is calculate the absolute error between each successive time step. And that's it. So we get spatial convergence before we move forward temporally. So if we come down and run this, delta t at a minimum for our configuration should have been 0.0825. Beautiful. What I'm actually going to do is come down here, set that. I'm going to comment this guy out, and we're going to do some funny things. I'll show you what happens when your time step gets too large. So if we evaluate the numeric portion of the code, it's a really simple explicit scheme, right? That's the meat of it. And you can see if you run this, probably one of the more beautiful surface plots I have seen in my life. We can see our temperature evolving as a function of time, and we see a very symmetric behavior about our midplane, both in our x and y directions, which is what we expect. It's a symmetric problem. I have to say, Bailey always wrote nicest commented codes, proper use of white space. She's been complimented by people at JPL and Caltech on having some of the nicest MATLAB codes they've ever seen. So we can thank her for providing this guy, as opposed to you guys looking at my ugly solution. Well, what we see, our temperature is decreasing as a function of time, and this is saying 237.46 seconds. I forget what the analytic was. Let me put this up top and see if we're close. This will be the... Oh, yeah, our analytic was 239.8951. So if you guys are really interested, this would represent .6% difference of solution. And I assume if you just threw in a few more control volumes within there, you would decrease that value. So the two-dimensional case isn't horrendous. And what's cool is, you can play with your time step. For the explicit scheme, we want a relatively small time step. Say you got greedy. Let's see what happens. That should all be defined. Min non-zeros time step if max t less than 10. Let's do this. Let's see if it will run from the start. Nope. Yep. So I think for us to play around with that, just the time step size was fixed to define the upper bound. But I encourage you, if you go through this process, see what happens if you do exceed that criteria, where your delta t is too large, because you're going to visibly see some really funny results come out. The information is going to be propagating from your boundaries to the center of your domain too quickly, and you're going to be over predicting the cooling performance, really. So the time it's going to take to reach that 10 degrees centigrade max within the system is going to be a lot less than what's actually happening. And that's just because that information from your boundaries moves way too quickly. So yeah, that's the finite volume method for the transient diffusion equation in 2 dimensions. I'd really encourage you guys play with this example a little bit, do some fun stuff. see what you can get the code to do, what you can't get it to do. And in the meantime, if you guys have any questions related to your homework, please stick around. I'll be more than happy to answer those. I'm just wondering why this keeps failing. And I'll dig into this. But besides that, we're done a little bit early for tonight.